Hello everybody, this is Sequence and Series, day number 3 on monotonic and bounded sequences. This is just another way to prove whether or not a sequence is convergent or divergent. So these two things have to happen. Right? It has to be monotonic, which means it's either always increasing or always decreasing. And it has to be bounded, which means that the sequence has to have some kind of upper limit and lower limit, which I'll show you the methods on how to do that in a minute. A couple things with increasing, decreasing. A couple ways you can show that a sequence is increasing. You can show that the next term is always greater than or equal to the previous term, or you can show that if I were to put u of n, some sequence, into function form, like we've done in the lessons past, then if I can show that the derivative of that function form of the sequence is greater than or equal to 0, that will always obviously prove that that would be an increasing sequence. Decreasing, very similar. If the next term is less than or equal to the previous term, or if the derivative of that sequence in function form is less than or equal to 0. Sometimes it's easier to use number 1 method, sometimes it's easier to use number 2. I typically err on the side of number 2, but sometimes it's ugly. So we got to pick our battles here, and let's get it going. Alright, so here you go. Here's limit definitions. Decreasing sequence, as shown here. This is just showing that the first term is larger than the second term, which is larger than or equal to the third term, etc. on down the line. Right? Increasing means that the first term is less than or equal to the second, and so on all the way down the line. Okay, it can be proven, like I said, by taking u of n plus 1 and subtracting u of n. If that's greater than 0, right, if u of n plus 1 minus u of n is greater than 0, then that means u of n plus 1 is greater than u of n. That means it'd be increasing. Right, if I take u of n plus 1 and I subtract u of n and it's less than 0, then that would mean that u of n plus 1 is less than u of n, which means our next term is less than our previous term, which means it's decreasing. Again, of course, the derivative idea also is true here. This would be increasing, and this would be decreasing. So let's check out an example here after we go over, I believe, the idea of being bounded. Okay, so we now know how to check to see whether or not a function or a sequence, depending on what form it's in, is monotonic increasing or monotonic decreasing. Now we need to check to see if it's bounded. So all that you do, right, step 1 is just check to see is it increasing or is it decreasing, monotonic, right? And then the second step is we're just going to check for what the value is when n equals 1, and then we're going to check to see what happens as it approaches infinity. So let's talk about boundedness. I just want to look at a sequence, right? Let's take a sequence. Here's u sub 1, 2, 3, 4, etc. and down the line. Let's say u sub 1 is here, u sub 2, u sub 3, u sub 4, u sub 5. So let's just say that this is monotonic increasing. Right? We've already proven it using step 1. We've shown that the derivative is always positive. Well, now what we know is that this lower limit, right, where this value is u sub n equals u sub 1. Right? Let's say the first term was 5. Right? Let's say the first term of the sequence was 5. And the limit of the sequence as n approaches infinity is 12. Right? If we have a lower limit and we have an upper limit that we're approaching, then it's bounded. So that would be monotonic increasing and bounded. So we could say that that sequence, whatever it is, would converge. Now, if a sequence doesn't meet one of those two criteria, here's an example. Here's monotonic increasing, but it's not bounded. It's got a lower limit of whatever the first term was, but it has no upper limit, right? It's not approaching anything. An example of that might be u sub n equals n squared over, I don't know, 2, right? Although it wouldn't look exactly like that. But so step 1, we've shown it's increasing monotonic, but step 2, it's not bounded. So since it's not bounded, that would not be a convergent sequence. Okay, let's go the other way. Let's say it's bounded, but it's not monotonic. Let's say the sequence looks like this. Right, something kind of oscillating, right? Well, it's bounded. It's got an upper limit and a lower limit. Okay. But really it doesn't, right? Because the limit as it goes to infinity doesn't really exist. But we'll just say, let's say for a moment it's bounded. But it's not increasing or decreasing. It's both, right? So it's not monotonic increasing or monotonic decreasing. Therefore, that would be a failure of the first step. So let's look at a couple of examples. All right, so let's show that this sequence, u sub n equals 2n minus 1 over 3n plus 2, is first of all monotonic. I'm going to guess it's monotonic, I don't know, increasing. Let's see. And then second of all, let's then look at what is the first term and where does it go as it goes to infinity. Well, that actually might be a decent spot to start. So let's start there. Let's see what u sub 1 is. Okay, u sub 1 is, let's see, I'm going to plug in a 1, so that'd be 2 times 1 minus 1 over 3 times 1 plus 2, which is 2 times 1 minus 1, which is 1 over 3 plus 2, which is 5. Okay, so that's u sub 1. Now let's take the limit as n goes to infinity of this thing. Okay, I'm sorry, if you heard that, that was my dog that just farted next to the camera, so that was not me, I promise. Not me. Alright, the limit as n goes to infinity of this sequence would be 2/3. Okay, so my guess is if this is monotonic increasing, well, it'd have to be, obviously, because the first term is 1/5, and the nth term, as we approach it, as n approaches infinity, would be 2/3. So I'm seeing something that looks like this. Okay, here's our first term. And then our asymptote that we're approaching, or the value that this sequence is approaching, is 2/3. And I don't know exactly what each of the next few terms would look like, but I'm going to guess it's going to approach 2/3 in that manner. I would say it's probably pretty clear that it's going to be monotonic increasing, but let's just prove it with our two different ways. So let's take u sub n plus 1 minus u sub n. That's going to be kind of gross. U sub n plus 1 would be this method. Oh, I'm going to like the derivative a whole lot more than this. So there's u sub n plus 1. Here's u sub n. Oops. Over, gosh. Okay, so u sub n plus 1 will be this. Alright, there's u sub n plus 1. Minus, let me put this down here to emphasize that's all one term, over u sub n. Okay, we got to do some work on that. Let's just simplify the left side here. That'd be 2n plus 1 over 3n plus 5 minus 2n minus 1 over 3n plus 2. Gross, I have to get a common denominator. That means I'm going to multiply top and bottom over here by 3n plus 5, 3n plus 5, and top and bottom over here by 3n plus 2, and 3n plus 2. There's a whole lot of work. Goodness. Okay, so then I got a FOIL. In the denominator, I know I'm going to have 3n plus 2. I'm not going to FOIL that piece. 3n plus 5. In the numerator, here, over here on the left side, I'm going to have 6n squared plus 7n plus 2. Okay, so if I FOIL that, and over here I'll have 6n squared plus 7n, convenient, minus 5. So the 6n squareds cancel, the 7n's cancel, and 2 minus the negative 5 is a 7. Okay, so I get this thing. This is u sub n plus 1 minus u sub n. Okay, so if n is greater than or equal to 1, will this thing be positive or negative? Alright, and it looks like it'll be positive. If I plug positive numbers in here and here, I'm just going to get a positive number. Alright, so I can say that u sub n plus 1 minus u sub n is greater than 0. Therefore, this would be monotonic increasing. Okay, a whole lot of work. Oh my gosh. What if I did the derivative of that? I'm going to do it. So let's call f of x 2x minus 1 over, what is that, 3x plus 2. Okay, so quotient rule. But if I can show that this is true, then I know I have a monotonic increasing function. Okay, so low d high, that would be derivative of the high times the low, minus the derivative of the low times the high, all over low squared. This isn't bad, you guys. I prefer the derivative method on this one. Alright, so I would get, looks like 6x plus 4 minus, convenient, 6x minus 3. Okay, so I just distributed the 3, not the negative, along with it. So the 6x's will cancel. And I get 7 over 3x plus 2 quantity squared. Oh my gosh, so much easier. Clearly, if n is greater than or equal to 0, then f prime of x will be greater than or equal to 0. Or I'm sorry, if n is greater than or equal to 1, then f prime of x will be greater than or equal to 0. Okay, so then you got to write a therefore statement. Therefore, since u sub n is monotonic increasing and bounded, then u sub n is a convergence sequence. That would be it. Alright, let's talk about a couple of other things here, and then we'll be done for the day. Alright, monotone sequences, we just went over this. Okay, so this piece here, if a sub n plus 1 is greater than or equal to a sub n, or if f prime of x is greater than or equal to 0, or if a sub n plus 1 is less than or equal to a sub n, also known as the derivative of the function notation less than or equal to 0 for all n, then you have a monotone function or monotonic sequence, right? So to show that a sequence is monotonic, you just do what we just did. Either show that a sub n plus 1 minus a sub n is greater than or equal to 0, aka increasing, or the opposite, aka decreasing, or alternatively, this is just the derivative method. Right? Monotone convergence theorem. A monotone sequence of real numbers is convergent if and only if it's bounded. So it's got to then be bounded if it's monotone, and then you have a convergent sequence. I think that's it. So why don't you have yourself a great day, and I will too. Peace out. Why not? Go have myself a little protein shake. And yeah, it's all good. Have a great day. See ya.